All right, well, my name is Paul Manning. I've been with VMware for almost 4 years. I'm part of our technical marketing group, and I'm focused on our storage technologies. So just to make sure you guys are in the right session, we're going through really sort of what's new in 4.1 for storage. And with that said, the very first screen here, I don't know if you guys have seen this one. There will be a quiz on this, by the way. Did you guys read that in about 3 nanoseconds, and we'll move on to the good stuff. My session is really about what we have today, so you don't have to worry so much about futures or projections, but our legal team wanted you guys all to be able to recite this by the end of the week, and it will be on the quiz. What we're really going to dive into, the subject matter I'm going to talk about today in this session, and then again, this is repeated 2 more times. I'm going to feel like at the end of the week, I'll be like sort of, in replay. We're going to talk about storage I/O control, which is really, in my view, one of the most game-changing features of 4.1, and we'll talk about how that works, where it fits, and more importantly, I think a lot of confusion about what storage I/O control does, because a lot of people think it does stuff that it doesn't. So that's one of the level sets I want to give. As well, there is a drill-down session, and throughout the slides, I have a couple of call-outs for other talks that go into greater detail on a number of these features. But the other one, this one is another 4-letter acronym, because storage I/O control is SOIC. We have VAAI, which is the vStorage API for array integration, and that's really leveraging the ability to offload some fairly I/O-intensive activities off to the storage array, let it do it, and then report back that it's been completed. So we'll go through some details about that. The third area is really the performance monitoring capabilities. Both ESX Top has new functionality and features, as well as through the GUI. We've added a number of new capabilities to make it easier to monitor where a choke point might be or some sort of troubleshooting, as well as diagnostics, particularly some screens added for storage I/O control that are very helpful in knowing when it's kicking in and how is it helping. The other topic is the Guzzi Enhancements, and there's an entire hour session that goes into a deep dive specifically about what's new for the Guzzi Enhancements that's called out in one of the slides. We'll go through and talk a little bit about one of the features are that were added, enhanced. And the last one, which in previous versions of this slide, I had it appear as I joked about, in white font on a white background. I didn't even list the 8 gigabit support, but I have a couple of slides that talk about, increasing the bandwidth, as obviously workloads get higher and higher and consolidation of more workloads on a given ESX server take place, our ability to support, larger pipes and for the Guzzi and NFS, the ability to have 10 gigabit, and then for the fiber channel to be able to support 8 gigabit. It's very important to have that no longer be a potential choke point. So with that, that's where we're headed today. Start with storage I/O control. I think the thing that's important about storage I/O control is to really frame where it fits and how it works. And the idea, some people initially thought it only worked with certain VMs that you had set shares versus ones that may be default shares. And we'll go through a little bit more about that. But the original idea was to be able to really try to control at the data store level such that a virtual machine could not take a lion's share of the I/O bandwidth. And in this example, we have 3 VMs running on 2 separate ESX servers. The online store and the Microsoft Exchange are what might be considered really business-critical applications. And then a data store running on the other ESX server may be sort of back office or reporting stuff. But if left uncontrolled, you may have 90% of the bandwidth being consumed by your data mining, and then your business-critical applications are left starved for I/O bandwidth. And in effect, what you really want to be seeing is the ability to have the pipe or the amount of bandwidth available from an I/O standpoint aligned with the criticality of that VM. And in effect, storage I/O control is a way of delivering on that vision. So the way we're doing it is really, everybody's probably familiar with the ability to have shares for your CPU and your memory. And with 4.1, we've added the capability of adding some more intelligence around data or shares for your disk, as well as there's a network I/O control, which if you haven't heard about, is an interesting talk on that, as well as in our expo hall, we have some demos around a network I/O control. So really using more of and that one we're actually, I may be going off a little bit off tangent, that's controlled at the distributed virtual switch, at that layer, not at a data store level, which to bring it back to this slide, in effect, shares have existed at a VM level and enforced at a host level. But in 4.1, we've brought that concept down to, you now have in this picture 3 separate virtual machines running on 2 separate ESX servers, and you have the ability to have those controlled at a common data store. So it's really taking it down from just a single ESX server, which is where they were supported and enforced prior to 4.1, and having them now enforced across all of the hosts that are in that ESX cluster or are sharing that data store. And that's where, as a capability, we can now set these shares at the VM level, or in most environments, it might be easiest just to leave them at the default. Typically, when you create a VM, you'll get the default value for shares is going to be 1,000. Unless you go into edit properties and change those, it will remain at 1,000 per VM decay. So a VM that had 2 virtual disks will have 2,000 shares, unless you go in and change it and either reduce or lower. But what we do with storage I/O control is we aggregate all of the virtual disks that are on that data store for that VM, and then start using that total number of shares as the metrics by which we decide how many I/O slots are given for the VMs that are sharing that data store. Now, by default, storage I/O control is actually not turned on. When you install 4.1, it is not enabled. You need to go in and actually on the edit properties, and this is under the data store view within Virtual Center. For each of the different data stores, you can actually see whether it's enabled or not enabled in some of the columns that show up on the data store views. And then to go in and enable it, there's that showing up there is where you set that on. And once you've enabled it, basically one important thing, and this is one myth, is it does not kick in until latency gets above a certain threshold. By default, our threshold for the data store is at 30 milliseconds. So what that means is unless you get latency starting to accrue, we're not going to kick in. We're not going to get involved. The analogy I think is probably the best and easiest to think about is if you have a carpool lane, you don't necessarily want to enforce the carpool lane until you have congestion on the highway. And in effect, until you start seeing the traffic slowing down below a certain speed, you probably don't want to have that one lane dedicated to high occupancy vehicles only. The same is true with storage I/O control. Until A, you've enabled it on the data store, and B, congestion gets above that threshold, it's not going to engage. Now, this is another one of the views for a given data store that is showing which virtual machines are, in effect, on or sharing that data store. In this case, we only have 2. But what we're highlighting on the right is the ability for that data store shares to be, in one place you can see that VM2 has got 70% of the disk shares, and in effect should be getting, when there's congestion, higher priority than VM1, which only has 30% of the shares. So in effect, if things were working perfectly, you'd expect 70% of the I/O bandwidth to be given to VM2, and only 30% of it to be given to VM1. And it's really in that aggregate and in this view that you can see what is the percentage of shares per VM. Now, going back to the example I showed earlier, we have the online store, which was, again, business critical, a high priority VM. We don't want it slowed down, as well as the Exchange server. And in this case, we may want the shares for the data mining, when congestion exists, to be throttled back and only given 2 I/O slots. And that's really the way in which these shares translate into how we use them and how it affects the overall I/O queue scheduling of the ESX server. Now, this one example is going to be kind of a little hard to read, maybe in the back of the room. This isn't a technical white paper, which I have a link for in this as part of our virtual or a VMware technical resources library. And if you look under storage papers, back when we launched 4.1, and I think July 12th would be the date, you'll find this one paper that was posted, or maybe it was the 22nd, I think it went up. And there's a good amount of write-up that shows this, as well as the other slide that I'll talk about next. But in this example on the left, we have machines that are essentially one virtual disk with the default shares of only 1,000. So in effect, we haven't gone in and changed any of the edit settings to change the disk shares. We've just left them as the default. We're running a pretty intensive I/O workload on it. I think in the case of the paper, it's an iometer pounding away at a pretty high rate of reads and writes. Now the attribute you see on the left is that because virtual machine, the third one, virtual machine C, is the only one running on that ESX server, it's getting roughly twice the bandwidth of the I/O bandwidth than the two that are sharing one. In effect, three machines equally working. What's gating the performance, you're getting 50% of the I/O because it's got all the queue depth. And as latency is pumped up a little bit, it's getting a higher percentage relative to the two VMs that are on the other ESX server. When we enable storage I/O control, you'll see on the right that 100% of the ESX I/O queue is actually throttled down. In effect, we've got only 12 queue slots available for that VM, which is in effect equal to what the other two get on the other machine. So it's really in that weighting of percent, in this case equal percent of shares, should only get a third of the I/O slots available, and to do that we achieve it by throttling back the number of I/O queues available on that second ESX server. Now you'll notice on the right, there's in effect what we're doing is we're now using a few less queue slots, so we're getting a little bit less throughput, but the latency drops down significantly. And it's that trade-off of throughput and latency that storage I/O control is managing in a way to ensure fairness and to ensure that one VM doesn't get more than the lion's share or majority of the I/O queues. Now, in this next example, if you notice on the top, we have 1,500 shares for VM A, 500 for B, and 500 for C. So in effect, you would expect the results on the bottom right, 60% of the I/O queues should be going to VMB because it's got basically 60% of the shares. The other two are splitting the remaining 20% available. Now, without storage I/O control on the left, you notice that without any regulating of that, 50% of those I/O slots would be going to VMC because it's the only one running on that ESX server, and that the other two are splitting what's available on it and only it. So in effect, if you take a look at that one on the left, that's the way shares were handled before 4.1 came along, and that you could change the shares, but it wouldn't really be looked at the data store level. It would only be enforced at the host level, at the ESX server. So that's, again, there's a white paper that goes through these slides in more detail and explains some of it in much greater detail. One example that isn't a performance study that we've done, it's also on our external website, takes a look at a case study where we have 5 virtual machines, and you notice the disk shares, second column from the right on that table. VM5 has 8 times as much importance as VMs 1 and 2, and I can't do the math for the remaining, but 3 and 4 are a little bit more important, but still not even 1,000 shares. So we've gone in, reduced the number of shares for the first 4 VMs, and then quadrupled the default number of shares for that 5th VM. Or in fact, it could be if there's 2 virtual disks, we've maybe doubled it, because again, shares are per VM decay aggregated for how many virtual disks that VM has in this data store. So in this example, what we've done is we've started out, the high priority VM number 5 is the sort of magenta or the pinkish color at the top there. It's running along and is ripping along pretty well until VM2 starts up, at which point it drops off 14%. Now, the thing is, at this stage, we still don't have enough I/O to kick in a latency that causes storage I/O control to engage. In effect, that 14% drop is a result of it, sharing the I/O queues, but we're not yet at a latency where that storage I/O control is kicked in. However, when we fire up VMs 2 and 3, which are the green and the blue, at this stage, we are getting congestion to the point that storage I/O control would be kicking in, but it's not turned on. So in this case, we are seeing a 21% drop in addition to the 14 that we've already lost. And a little bit later along comes VM4, which is this purple one just above the T in time, and we drop another 15%. Now, the aggregate of these weighted for the appropriate statistical analysis is VM5, our most important application, without storage I/O control, has been effectively rolled back 42% from what its throughput was unobscured. Now, when we take a look at what happens with storage I/O control, running the exact same workload, scripted iometer, kicking away at these different VMs, We have a 14% drop, which I mentioned again. Storage I/O control is not yet engaged because the latency hasn't kicked up to the threshold. However, when the other two VMs, 3 and 4, come in, I'm sorry, it's 2 and 3, the green and the blue come in, we only see an 8% drop. And then as the fifth one, which is number 4, comes on, we see another minor drop, but again, it's only 22% relative to the 42% we saw without storage I/O control. So there's a study that goes through a lot more details, and if people are interested, this is talked about in one of the storage I/O control talks, actually the storage I/O control talk that I'll refer to later in the slides. But this is important to understand sort of the weighting and how it's using shares to be able to determine, not at a host level, but across all the hosts sharing that data store, who gets what bandwidth. And then there's sort of a drill down. It's not in this slide deck, but 22% relative to it is compared to the previous one. Now, again, a lot of discussion and debate went into, well, what's the perfect threshold for when that latency should be causing storage I/O control to kick in and begin actively managing those I/O queues versus when it's not. And at one point, I think in the beta, we had it at 40 milliseconds. We dropped it to 35, and in the GA, we went with 30. There is sort of a curve where you begin to add more and more I/O, and the latency begins to sort of go up through the ceiling. And ideally, you want to have your threshold set such that it's before that latency really starts to kick up. And in effect, you want to throttle back so you're getting at sort of the beginning of the inflection of that curve. Now, there's a lot of debate about whether that curve really tails off and decreases or whether it sort of goes flat. I'm going to leave that debate. And I've used this slide from somebody else, so I'm going to take no responsibility for the flatness of it. But the point here, and I have a couple slides that maybe help clarify what I'm talking about a little bit more. The one point I want to highlight here in the changing the default threshold values is we give people enough rope to hang themselves. If you start playing with that latency too much, you can actually, if you lower it too much, you get storage I/O control engaged early, and it's over managing the process. If you get it too late, latency is already going through the ceiling. So there is a bit of a debate, and especially when you look at some of these auto-tiering storage devices, where they might automatically be moving a LUN around the back end between SATA drives and fiber channel drives, or a variety of different ways to sort of do self-healing within the array. At one point, we were considering saying we won't support those, but in a lot of testing we've done, we found that they actually do work quite well with storage I/O control. And some of our beta customers who were testing it found that the SSD, SATA, and these auto-tiering arrays worked quite well. So at GA, we decided to just support them. But you do have the potential of a dog chasing its tail, in that if you're trying to sort of throttle things around and the array is trying to move a hot disk into different areas to increase performance, you get a little bit of confusion as to who's doing what, and the benefits of it can be a little bit convoluted at times. But for the most part, it does work and is compatible. This next slide is really, I remember when I was studying physics in college, I was sort of falling asleep in the back row when the professor started talking about fluid dynamics, and he used the example of a beer keg. And I immediately stood up, sat up in my desk, and started taking copious notes. And this funnel analogy is remnant of the professor who woke me up. If you look at throughput and a funnel, imagine a disk is, a container, for this example, a large beer container maybe. And there's a point where as you start pouring stuff into it, you hit what's called maximum throughput. And that's determined by how wide the opening is. And what happens if you keep increasing the flow is you get to the point where you've exceeded that throughput and you start backing, the funnel starts filling up. This is essentially the analogy where latency, and this is really more write latency as opposed to read latency, because that's maybe confusing my analogy here. But what's happening is once you've exceeded that max throughput, you begin having to start to back up into the funnel. And the larger and larger the higher and higher that funnel gets filled, the longer whatever fluid is at the top is going to take before it gets down into the container. And the same basic concepts are true with storage, in that once you've exceeded that max throughput, you start actually queuing things up, and latency starts to go up because it can't keep up with the inflow. Now, what storage I/O control is doing is effectively trying to regulate, and in this case I'm using 3 arrows, start throttling some back to lower the level within the funnel, to allow that latency to get back down to a level, and then determining which of those VMs, which of those 3 arrows is getting what percent of the total throughput available. The challenging part of storage I/O control is you can measure latency at the data store, which is what we do when we determine whether to kick it in or not. You can measure latency at the ESX server level, and then you can measure latency at the guest OS. And so these 3 different places that you can measure it are often confused by people. You'll have somebody call up and say, hey, my VM's really slow. Well, it could be that you've exceeded max throughput at the data store level. It could be you've exceeded it at the ESX server level, or it could be that VM is just not configured correctly, and maybe its virtual SCSI is exceeding what's available to that one guest OS. But it's important, I think, the analogy here, when you start looking at, if we go back 2 slides, the point of this inflection, when we talk about the green arrow, the congestion threshold, when you want to have your you want to have storage I/O control to kick in and start regulating it, really comes down to where is the point where that latency starts to ramp up quickly. And if you can keep the funnel such that maybe you've got a little bit of backlog, but it's going to be pretty efficient, versus you're about to spill over the top of your funnel, that's where you get a lot of latency complaints and problems. So I hope that funnel analogy helps. It's important to understand that trade-off between where latency kicks in and at what point that threshold, for example, off to the right there where the top of the arrow, if that's a point where your disk array for this device is showing 30 milliseconds of delay, you don't want it to keep rising because then you have more and more people congesting. And what we are doing is throttling back and controlling the I/O queues at the ESX servers. In this case, I'm showing really sort of 3 ESX servers, but it could be up to 32 or whatever number is connected and sharing that data store. This is a reference to the materials that are available on our external website, the technical paper. There's a concepts and deployment considerations that I co-authored. And then there's this performance study, which has a really long name. That's not the full title of it. But there are both there. Those links are, if you go to our technical resources and just remember the 5-digit number, and if you picked anything and replaced the URL with those 5 digits, you'd have a pretty quick hit. But again, they were posted in July, if you can search for any number of ways. The talk that I would like to plug for anybody who wants to get a real in-depth deep dive of the performance and the internal mechanics of how storage I/O control works is this paper, TA7994vStorage. It's repeated 3 times and hasn't yet happened today. So it's tomorrow at 2, Wednesday at 1:30, and Thursday at 3. If anybody wants to take note and do that. Any quick questions on storage I/O control before we move on? Yes? Question is, does storage I/O control kick in independently in reads versus writes? And the answer is no.
So either one is 30.
Yes. If the latency at the device level gets above that, it will kick in, regardless whether your latency is a result of slow reads or slow writes.
And does it pops over, latency all over the board generally?
There is an... Yeah, I'm going to refer you to the talk here where they're going to go into the extensive algorithm and probably have you sign a non-disclaimer to show you the real secret sauce. But no, there is an averaging algorithm, and I'll show you a couple of charts at the end of the performance section that shows how some of that normalization is being calculated. We had a question in the back? Yes?
You have to put the host in maintenance mode before you do it on?
You do not have to put the host in maintenance mode. It's a data store attribute, and it can be toggled on or off and is handled live without interruption. Yes?
Is there any ability to schedule a difference in the waiting factors based on time of day?
Not that I'm aware of, but if you go to that talk and ask the engineer, that might be a feature. I'm sorry, the question was, is there ability to have it change values for different times of day, and in effect maybe be more sensitive during the business hours and less sensitive? I suppose you could actually probably write some cron job that went in and changed through the command line interface at a certain time of day, but I'm not sure that would be technically supported. Yes?
I'm assuming there's a reason why it's not enabled by default. Is there a problem
the question is there a reason that it was not enabled by default? And the answer is the engineers lost a coin toss. I'm not aware of any. No, it was considered to be a new feature, and that we should turn it on for those who want it and leave it off for those who didn't. Yes. Well, basically, it's on a data store by data store level. So there are people who you can take VMs and have virtual disks on multiple data stores, in which case you do get into that mix and match mode. You could also vMotion a VM or storage vMotion a VM from one data store that has it on to another data store that doesn't, and that's transparent. I think it's predominantly looking at monitoring your performance metrics that you would see the difference and determine whether you want to use it or not. Yeah, one more, I guess 2 more questions and we'll move on to the next section. Yes? Does not. Basically, in 4.1, it is for block-based storage only. It does not work for NFS. This is where I guess I have to straight to slide number 2. It's on the roadmap and under consideration for a future release. Yes? Yes, that is the first of that, as my colleague calls it, the chiclets slide. Or no, I'm sorry, the Skittles slide with the bright colors. They look like those fruit chiclets colors. That first one is the case, and in that best practices or concepts paper, it talks through how there is a distinct benefit in effect of keeping one VM from getting the lion's share of I/O, even if you haven't gone in and changed your shares for your disk shares. Okay, we're now going to move on to the second subject, which is the other 4-letter acronym, VAAI, which stands for vStorage API. And I know this is kind of breaking rules because an API is already a TLA, or a 3-letter acronym. And so we're putting a TLA into a 4-letter acronym, so you have a TLA within the FLA. But anyway, it's sort of a remnant of IBM, I think, alphabet soup. But the key thing to think of it is array offload. In our 4.1 release, that's really the key value prop. We're taking certain I/O-intensive things and allowing the array to do it because it can do it more efficiently and not have a lot of stuff go back and forth. Now, the 3 primitives we are supporting in the VAAI, which maybe I should start with the bottom. In the initial 4.1 release, it is block-based storage only, so iSCSI data stores and fiber channel data stores. It is under consideration for VAI being a NFS data store in a future release, but not yet statable when. The 3 primitive, actually the other part, bullet number 2 near the bottom, is it requires firmware. There is a handshake that needs to take place between the ESX server and the storage array for this offload to function. In other words, there's a version of the storage vendor's firmware that needs to be resident on that storage device for this feature to be supported. It is on our HCL, so our hardware compatibility list shows those. Today, I believe it's 6 vendors that have that firmware available to leverage this capability. But to come back to the top, the 3 primitives are an ability to do a full copy. So this is in the use case of cloning a virtual machine or deploying from template. Or the other one is a storage vMotion, where you can actually have the copying take place within the array and take out the step of having to copy it up to the ESX server only to write it back down to the same storage device. The second primitive is a block zeroing function. The primitive is actually also sometimes known as write same. And if you imagine you're zeroing out you're creating a eager 0 thick disk, which basically at the time you create it, it's zeroed out and initialized. This would be, for our fault-tolerant technology, a requirement that FT have a eager 0 thick disk. You can have the array go do all the zeroing and move on to the next step and not have to wait for the array to come back and pause until it's done the zeroing. So in effect, the block zeroing is that second one. The third is this hardware-assisted locking, which is effectively using this primitive called atomic test and set to be able to have a much more granular means of updating the metadata for a VMFS volume. So in effect, for our block-based storage, where we're formatting the disk and VMFS is acting as a clustered file system, this hardware-assisted locking is, instead of using a SCSI reservation to lock the entire device against updates for a very brief period of time, we're able to just go and update a very small segment and using atomic test and set, be able to do that much more discreetly and more efficiently. Yes?
So these require APIs to be supported on the storage side. What storage vendors did you know of that these?
Well, in effect, the 5 that EMC has a firmware release for it. NetApp has a firmware release for their fiber channel connectivity. I know I'm going to forget one. HP, HDS, and IBM. I think 3PAR is the other one that it's imminent, and others to follow. Did I forget anybody? Dell through, I think Dell EqualLogic is either there or there soon. But yeah, that was on my version of slides, and then somebody ripped it out for, I think, because of slide number 2. So this sort of goes through a little bit more details about the use case. You know, the process of creating a VM from a template you're deploying, you know, typically 100 gigabyte VMDK may take 5 to 20 minutes to copy. If you're using this full copy technique, it basically can be done within the array much more efficiently, much faster, and you know, speed up to 10 to 20 times is not uncommon. The second one that's a little easier to talk to or conceptualize is storage vMotion, where you're basically moving a VM home, as represented by the manila folder, from one data store to the other. They happen to be in the same array, or even with certain arrays, you know, within the same collection of arrays that are supported by the firmware, you have the ability to actually have that copy being done without coming up to the backplane of the ESX server, only to be written back down. And here, you know, significant speed up, again, can be had. This next slide, I think, points out the benefits of the ability to do a vMotion with the primitive turned on versus it turned off. I think actually it's the other way around. Turned off, it took 2 minutes and 21 seconds, as noted with a, you know, recent tasks time, to move this VM from one data store to the other while it was up and running. And then with the primitive enabled, ran it again, and it only took 27 seconds. So it's significant, you know, 241 versus 20, it's significant speed up. Now, this is one of the demos we have in the click-through down in the booth as a demonstration available to show this. And there we're actually creating a Eager Zero thick disk with the primitive turned on and without it turned on, and comparing those two. Question?
Is enterprise cost required for this?
I believe it is, and I have to say I'm not a sales guy. The packaging, I believe this is the vStorage APIs, which includes the MPP module and some of that, was Enterprise Plus, and my understanding is it has not changed, but I'm the wrong guy to ask. It is. Okay. Yeah, the last time I said that, tomatoes were thrown at me, so maybe I should. The point of... What's that? Converter and cloning.
Do they support this?
My understanding is for the functions that would be able to leverage those 3 primitives, it would. But I may have to come back to you on that one. I mean, basically, this is at the ESX server level, so it's really low down in the stack, and I think Converter and you know, the other tools are leveraging some of these primitives from a higher control point. So I believe they do leverage it, but I'm not 100% certain. This slide really is pointing out the fact that, you know, clock time is what most people focus on. How long did it take a task to complete? But it's important to also look at how much CPU and memory was required. As you're really loading up and consolidating a lot of servers, you know, what is the impact on your infrastructure in terms of memory, in terms of network and storage? And the comparison here is that by virtue of offloading these moves, this is more for the full copy primitive, you know, it's not only faster in terms of the time it takes, but it's more efficient at freeing up memory, network, and CPU, and disk I/O. So that there's a real benefit in doing it with the VAI offloading. Now, one of the interesting talks I attended this morning, ESX Top, our command line utility, actually has some metrics that were added to be able to show you exactly which these primitives helped, you know, offload and how functional or efficient some of the speed up was. And so there's some good integration there. The Eager Zero thick, which again is a requirement for our fault tolerant technology. You know, if you create I mean, by default, and I may be going a little bit of a rat hole here, but by default, when you create a virtual disk, it is lazy zero thick, which means whatever block size that VMFS volume has been created, we will zero out the first block, and by default, it will be a megabyte. And as we fill that up, we've already allocated the contiguous space, but we do the zeroing as we go. Whereas if eager zero thick or for fault tolerant, when you create it, you carve out all the space and then you initialize it by writing zeros to the entire content of that virtual disk. So the efficiencies you gain, there was an interesting study comparing thin provisioning to non-thin provisioning, and one of the things that was detected in that is the concern about the time it took was more a function of the difference between eager zero thick, which is fully initialized, versus the lazy zero thick, which is initializing every time you go to that next contiguous chunk of a block size, typically 1 megabyte. But the point is that in this process, if you're doing eager zero thick, you're allowing the array to go off and do the zeroing out, and it will report back, but it effectively allows you to take control and go on to the next step. So that speed up is significant, and that's the demo in the booth. If you come to the infrastructure section of the VMware booth, 716 down in the expo hall, which opens in exactly half an hour, you'll be able to see that. So again, this is a benefit that is there. The third primitive we'll talk about is the scalable lock management, and here's where, again, as I mentioned, VMFS being a clustered file system, we have to make sure we don't allocate free space to 2 ESX servers to give to 2 separate VMs at the same point in time, because that would be corruption. You'd have disks, space that's being written to by 2 separate processes, and guess what? One would overwrite the other, and it would be kaput. So what we have been doing in VMFS is using a SCSI reservation to briefly lock writes. It's still readable, but we can't write or update for a brief moment in time while we update that metadata to say that this space has now been reserved and given to that process. So, there are a number of things that do trigger a SCSI reservation. Even when you start a VM, you have to create your vSwap space. That comes out of free space. When you delete a VM, you've got to return those files back into free space. So that metadata is effectively the metadata for your file system is being maintained, and its integrity is very important to the reliability of the entire data store. So the VAI hardware assist is leveraging this, again, atomic test and set, which is able to, in effect, make a change, test what the value was, make certain that when that change is now committed, that hasn't changed from what it was when you first tested it. And so it's a much granular, more efficient way of doing that. One of the areas I think this will show up the most in terms of usability is if you're using our lab manager technology or whatever we decided to call that in a future release, and doing rapid deployment of a lot of VMs and a lot of virtual disks and whatnot. This is where you see the scalable lock management typically really add a lot of scalability and throughput. We've done a lot of enhancements to make our use of SCSI reservations more efficient, particularly in 4.0 when we came out with thin provisioning. We reduced the number that we took and the amount of time we take. So typically, most environments don't even run into the consideration of SCSI reservations causing scalability concerns, but occasionally that does come up, and it's an area that people need to understand. This will help it increase higher scalability, and that's a good thing. So that is the slide sort of reiterating what I've already spoken to, granular. Yes, a question? I think distinctly, and some of our beta testing of this, initially VAI was not part of the beta test version 1. In our second version, or second release of the beta, or refresh, a number of customers were testing that. Was one of the areas, because in effect a backup, you're typically having to lock do a SCSI reservation to go make sure you're getting a point-in-time copy of where all the disks or all the entities of a VM are. And this would definitely help in the efficiency of that. There are a little bit more details here. The one real zinger that threw me is if you look in the table of contents, which is what that other the TOC is, your table of contents, in the ESXi documentation, the configuration guide, chapter 9. If you try to find this feature in the table of contents, you've got to look for storage hardware acceleration. VAAI didn't quite make it in the table of contents. But then under the settings, if you go to advanced settings, the way you turn these features on and off is under the data mover and then the VMFS, the three different primitives. You can toggle them on and off. Again, by default, they're not turned on. So if you the firmware is discovered, I'm sorry, maybe I got that backwards. I think they are turned on. If the firmware is discovered, they are enabled, and then you can turn them off. So it's opposite of storage I/O control. It is enabled by default. Now the other one, Seth is one of our engineers, is talking about this. I don't have the exact times for TA7121, but that's where get a full drill down, an hour-long talk on this for those of you who want more details on that. And I believe his talk is tomorrow morning, so again, you have two chances to listen to it. Now we move on to the third topic, and the time check says that we are now 38 minutes in, so I've got to wrap up in 7 minutes, right? Now, the majority of our efforts in 4.1 for performance monitoring was really to try to have some higher level of parity in terms of what capabilities existed in NFS as did in block-based storage. And we've added a number of screens of capabilities to enhance that for both the ESX top and our ESX top for the ESXi implementation, and then also through the GUI, and adding a little bit more granularity in terms of how you can drill down to do troubleshooting and more graphics. This table is really sort of showing you at the object level, either VM or at ESX server, what are the components that you can get drilled down, and then whether they exist. The ESX top on the far right is the command line, or through the GUI is vCenter. The one big splat that you'll see in the first line and the second to bottom is for the case of block-based, if a LUN is a data store, in other words, if you haven't aggregated multiple LUNs under one data store, what you get at a LUN level is effectively at the data store, and so that's why there's a little bit of a call out on that. But this is maybe more for reference to show you sort of some of the details. With ESX top, we now have the ability to show the NFS information that's pertinent. Our latency, we don't have the ability to show at a device level because of NFS, that's not being exposed, but in terms of the number of reads, writes, and some of the other things you get from ESX top, that's available. Through the GUI, we're now looking at a ESX server and being able to look at the I/O activity on both reads and writes. In this case, we have two separate data stores that are being accessed by that ESX server, and we're showing here over a period of time, the reads and writes. So you can see the red is effectively read latency spiked at one point. And the benefit about the GUI is that you have the ability to look back in time. It's not like the dashboard of your car where your speedometer tells you how fast you're going now, but not how fast you were going 10 minutes ago. So this is helpful in being able to troubleshoot, maybe a disgruntled user's calling in and saying their data store their VM had a really slow thing. You can look back and find out, was there a spike? This one is also now showing for block-based storage the ability to get host statistics, so at ESX server level, to be able to see at the storage adapter as well as at the storage path what the latency is and read-write throughput. So a little bit more granularity there. Here we're showing at a given VM, as indicated by that first of the three showing up. We're able to now look at what is the I/O for a given data store. And in this case, we have two separate data stores, and we're looking at read and write latency. Here we're now going down even another level, going down to look at the virtual disk, the virtual disk layer for that given VM. So in effect, you're getting a little bit more drill down for the granularity. Now this is the one that I talked about for storage I/O control. We've added 4 new charts that are helpful in understanding if it's kicked in and how it's handling it. I'll start by the top left is the normalized latency for that data store. Now, if storage I/O control is not turned on, this will be all zeros. The normalized number is only calculated if and when the storage I/O control is enabled at the data store level. And then if that number gets above your threshold, it's kicked in. When it gets below, it's not on, or it's not in effect engaged. Now, on the bottom right, what we're showing there is for the 2 ESX servers, what is the queue depth of those different servers. So in the case, you can see the yellow bar is got more queue depth assigned to it than the green one. What that means is we're throttling back the I/O on the blue server, which is the IP address there on the bottom, to be able to allow more I/O slots available for the server that's represented by the yellow bar. And you can see if you change thresholds, or in one case on our demo, we actually can set the limits for a number of I/Os per VMDK, and you can see that number dynamically change to address the balancing and rebalancing of the I/O queues for that workload. So these views are very important in being able to really look at what's happening and how is that change, how is it adjusting to effectively equalize the shares or enforce the shares. Now, we're coming into the home stretch here. My iSCSI slide is not extensive. I'm pointing you to a talk that's been given by John Hall and Andy Benta that, again, an entire hour going into what is new in the iSCSI. But in effect, I think the high-level ones, there's a boot from iSCSI in the software, or the boot from the iSCSI software and shader. There's the offloading available. In effect, through a Broadcom card, we have the ability to, instead of having either a hardware-based iSCSI card or a NIC that we're doing all the translation from the SCSI commands down to the NIC commands within the vKernel, we've got a hybrid, and that's available as well. More session management and some new command line interface utilities to be able to manage and monitor the iSCSI traffic. This is a little bit more detail around the booting from software iSCSI. So our ability to go through and make sure that NIC supports it, so on the HCL and the configuration steps. This is outlined in a couple of different areas, but it's a new feature that's highly considered to be, particularly for blade servers, very important. And then the final topic here is around the use of 8 gigabit HBAs. This is really more a certification effort that we've done to validate and make sure this works throughout. This chart is showing, for larger block sizes, you are getting effectively twice the efficiency and able to use the extra bandwidth. But again, this is something that as you start going into space, make sure you check the hardware compatibility list to make certain that your device, your HBAs are on that. So we wrap up with a quick summary and then a couple of marketing slides. Mainly the things we've added to 4.1 are enabling more applications to be virtualized, higher levels of consolidation on a smaller number of ESX servers, and then also ability to have better visibility into doing performance monitoring and capabilities to really help size your environments more appropriately for your workload. The three takeaways, I had one nice, really fun version of that said, there's curves in the road ahead and watch out for, stay away from the light. But the marketing team brought me back to these, which are really, I think it's in many respects, there's a lot of benefits to 4.1. Encourage you to migrate it. With storage I/O control, a lot of the customers who are doing the beta testing, some early adopters are saying, we just turned it on and it's great. It works fine. And then the integration with the partners enabled via AI, I think, affords a lot of scalability. This is a plug for our ESXi, which I want to make sure everybody understands that after 4.1, we will not be shipping ESX Classic. So in effect, you got to start, thinking about how are you going to migrate and operate with the ESXi architecture. And there's more information here. And the final slide is, please fill out the surveys and tell us what you liked and didn't like about what we were talking about. So I'll be around if there's questions. Thank you.